Have you ever wondered how the continuous, seamless flow of sound from your voice gets magically trapped inside a computer, manipulated, and then sent right back out into the physical world? Well, let's dive right into this explainer, because bridging that gap between our physical, analog reality and the discrete, digital systems that power our modern world entirely relies on the foundation of digital signal processing. And today, we're going to decode exactly how that happens.
Here's our roadmap for the explainer. We'll start with what signals actually are. Look at their dimensions, compare analog versus digital, categorize processing systems, and finally, bridge the two worlds.
What are signals? The physical reality. The absolutely crucial point to grasp right away is that a signal isn't just some abstract math equation. It's an actual physical variation, like acoustic pressure in the air or the changing brightness of light, that carries real, meaningful information. It's the pattern of that physical variation that actually matters, and to work with it, we represent that pattern mathematically as a function.
Section 2. Dimensions of a signal. Let's build some complexity.
Think about a one-dimensional signal. Imagine the literal, physical waveform of someone speaking the word signal. Here, the acoustic pressure of a human voice, which is our dependent variable, varies purely over a single independent variable, which is time. It's essentially a straight line forward, continuously recording the air pressure at each passing fraction of a second.
Now, stepping up to 2 dimensions, think about a standard black and white photograph. It doesn't track time at all. Instead, it tracks brightness across physical space, using an X and Y axis. By mapping the exact intensity of light at every single coordinate on that grid, we form a complete 2-dimensional image.
And we can even scale this whole thing up to 3-dimensional, multi-channel signals. A standard color image maps different channels, specifically red, green, and blue, across physical space to create the vibrant, full-color representations we see on our screens every day. But, to keep our foundation rock solid for this explainer, we're going to focus our attention strictly on one-dimensional signals. We'll be looking specifically at situations where the dependent variable is amplitude and the independent variable is time. Honestly, mastering this one-dimensional flow is the absolute key to understanding the whole shebang.
Section 3. Analog versus digital signals. This is the core contrast.
There is a really stark mathematical contrast between these two worlds. A continuous time signal, which is what actually exists in nature, defines an amplitude value for every single real-valued moment of time. It's infinitely smooth. A discrete time signal, on the flip side, only defines amplitude at specific, isolated, equally spaced integer points. So it's a collection of snapshots, rather than a continuous flowing movie.
When you compare them, the continuous time analog signal is a completely smooth, unbroken flow. But the discrete time digital version, it's chopped up into isolated stems. In the analog world, time is a continuous physical axis. But in the discrete world, time has essentially been replaced by a simple integer sample index.
So how do we actually get those isolated stems from a smooth curve? Well, we use something called periodic sampling. We take a snapshot of the analog signal at a specific sampling period, which we denote as t. The sampling frequency, or fs, is simply 1 divided by t, giving us the number of samples taken per second. But there's one more crucial step to make it truly digital. Those sampled values have to be truncated or quantized to a finite precision. It's kind of like rounding off a really long decimal, simply because our digital systems only have so much memory to work with.
Section 4. Categorizing processing systems. How we actually manipulate the data. The fundamental flaw with analog processing is honestly pretty fascinating, because an analog system relies on a continuous physical voltage or current that is strictly proportional to whatever quantity it represents. The exact value is critically important. That means any tiny random fluctuation, like any background noise at all, directly alters the exact value. This makes analog systems highly vulnerable and super easily corrupted. Because of that vulnerability, the actual math inside these systems is completely different. Analog systems have to rely on complex calculus, specifically continuous integration, to track infinite voltages. But digital systems? They simply use accumulators to tally up a sequence of discrete numbers. It's a massive, game-changing simplification.
Section 5. Bridging the two worlds using interface systems.
This translation between worlds happens in 3 distinct, honestly beautiful steps. First, an analog-to-digital converter, or ADC, samples the continuous real world and converts it into a sequence of numbers. Second, the digital signal processor, or DSP, works its magic, mathematically transforming that sequence through digital computation. And finally, a digital-to-analog converter,
The DAC uses interpolation to reconstruct that sequence back into a continuous physical form that we can actually hear, see, or interact with. This creates a totally complete circular journey for our signal. The physical signal enters from the continuous world, passes across the boundary through the ADC into binary logic, gets processed, and finally flows back across the boundary through the DAC to return to physical reality. It's just a constant, endless loop of translation, manipulation, and reconstruction.
We've covered a ton of ground in this explainer, breaking down exactly how we map our continuous physical reality into the rigid numerical logic of computers. But as we wrap up, I want to leave you with a final thought to ponder the next time you look at your digital devices. Since we are quite literally chopping reality into isolated numerical samples to process it, what subtle, continuous truths of the universe are we forever losing in those tiny, microscopic gaps between the stems? Thanks for exploring this with me.